Rational functions. Our objective is to identify excluded values of rational functions, as well as graph rational functions. Who uses this? Gemologists can use rational functions to maximize reflected light. Let's start with some vocabulary. A rational function is a function whose rule is a quotient of polynomials in which the denominator has a degree of at least 1. So rational functions would be like y equals 2 divided by x, y equals 3 divided by the quantity 4 minus 2x, and y equals 1 divided by x squared. Notice how in each of these your variable is in the denominator. Some examples that are not rational functions would be y equals x divided by 4. Notice how the variable is in the numerator. Or we have y equals 3 times x. For it to be a rational function, the variable has to be on the bottom. So we have an excluded value. An excluded value is any x value that makes the function value y undefined. So if we put a 0 on the bottom of this y equals 2 divided by x, if we substituted 0 in for x, that would make y undefined. So that would be an example of an excluded value. It can't be an answer. Couple more vocabulary words. We have a discontinuous function. Their graphs contain one or more jumps, breaks, or holes. Meaning you can't draw the graph with a nice fluid line without picking up your pencil. So it's discontinuous. So at some point in time while you're drawing your graph, you pick up your pencil and then you put it back down again. An asymptote is a line that a graph gets closer to as the absolute value of a variable increases. So an asymptote, the graph is going to get closer and closer and closer and closer, but it will never actually pass that line. So let's take a closer look at that. So let's look at the graph of y equals 1 divided by x. The denominator is 0 when x equals 0. So 0 is an excluded value. This means there is a vertical asymptote at x equals 0. Notice the horizontal asymptote at y equals 0. So, there's a couple pieces here. When you look at your original function, you can decide or determine where your asymptotes will be located. So if it's in the bottom here, so we have y equals 1 divided by x, the denominator is going to give you your x asymptote. So your x equals 0 asymptote, which in this case would be vertical, or almost every time would be vertical. And then you have y equals 0. That comes from what's next to it. So when we had like a plus c value, for example, that is what determines where the asymptote is. So now let's look below to see a better example of this. So we have the graph y equals 1 divided by the quantity x minus 3. And then we have plus 2. So we want to find our x equals, so we want to find where our vertical asymptote is. So what would cause the denominator to end up equating to 0? Well, in this case, it would be 3. So we're going to have a vertical line at x equals 3. And that's one of the lines that the graph is never going to cross. And now we look at our plus 2. That's going to give us our y equals portion. So in this case, y equals 2. So we're going to have a horizontal asymptote at y equals 2. And that's the other line that the graph will never cross. Asymptotes are a great way to start drawing your graph so that way you have a better idea as to where your graph can't cross. It makes it a little easier. So now let's take a more formal look at identifying the asymptotes. So a rational function in the form of y equals a divided by the quantity x minus b plus c has a vertical asymptote at the excluded value. So whatever value is going to make the denominator 0 is your excluded value. And a horizontal asymptote at whatever this C value is. If it was 400, you would have an asymptote at 400. So let's look at an example. You have y equals 2 divided by x. If you need to, you can add a couple zeros in there to make it a little easier to see. So you're going to have a vertical asymptote at 0, because that's what's going to make your denominator 0. And then you have a horizontal asymptote at plus 0, since there's nothing being added here. And then if we had numerical values in, we would have, if we had 1 over x plus 2, what would cause the denominator to be 0? In this case, negative 2. So you're going to have a vertical asymptote at x equals negative 2. And your horizontal is whatever your C value is. So in this case, plus 4. So you have a horizontal asymptote at y equals 4. Let's start by practicing identifying the asymptotes before we start throwing them into a graph. So our x equals, or our vertical asymptote, is going to be at whatever is going to make our denominator 0. So what minus 6 gives us 0? Well, in this case, 6. And now we want our y. So we want our horizontal asymptote. And to find that, we look at our C value. Well, there is no C value. So if there is none, we can always think of it as plus 0. So our horizontal asymptote will be at y equals 0. Let's step it up a notch and see if we can do B. So we have our x. So that's our vertical, but we want to make this 3x minus 10. We want to equate that to 0, so that way it's undefined. So we're going to go with 3x minus 10 has to equal 0. So we're going to add 10 to both sides. So we have 3x equals 10, and then we're going to divide by 3 on both sides. So x is going to equal 10 thirds. So we're going to have a vertical asymptote at 10 thirds. And our y is whatever our C value is. In this case, minus 7. Now take a moment, pause the video, and try these 3 on your own. When you return to the video, the answer for each will be revealed. And there you have it. To graph a rational function in the form y equals a divided by the quantity x minus b, then plus c, when a equals 1, you can graph the asymptotes and then translate the parent function y equals 1 over x. However, if a does not equal 1, meaning your numerator is something other than 1, the graph is not a translation of the parent function. So when the numerator is not 1, you're going to have to make a table of values, plot your points, and then draw in what you need. Let's practice. Okay, so we have y equals 2 divided by x plus 1. Since the numerator is not 1, use the asymptotes and a table of values to graph this. So let's start with our asymptotes, because that gives us a good idea of where our graph ends up locating. So we want the vertical and the horizontal. So we're going to look at what's going to make our denominator 0 and what is our C value. So in this case, we have x equals -1 and y equals 2. You can draw these in with a dashed line. So one's going to be vertical and one's going to be horizontal. Then you can make a table of values. So we're going to choose x values on both sides of the vertical asymptote. So we have -3, -2, -3/2, -1/2, 0, and 1. And we simply substitute those in for x and solve for y. And when we do so, we end up with -1, -2, -4, 4, 2, and 1. So now, with your asymptotes and your coordinates, you have a graph of a rational function. So your dashed lines are the asymptotes, and then you plot in your points. Let's try another one. So we have y equals 1 divided by the quantity x minus 2, and then minus 4. So let's start with our asymptotes. We want to get our denominator to be 0, so we have our vertical. So we have, in this case, x is going to equal 2, and then our horizontal will be y equals -4. But what's really cool about this function is notice how there's a 1 as our a value, or a 1 in our numerator. So therefore, we can just translate our parent function. So we can just translate our y equals 1 over x. We don't actually have to make a table of values. However, if you can't quite remember what the parent function is and what it looks like, you can always make a table of values and get what you're looking for. So draw in your two asymptotes and then draw in your parent function as though that is your new coordinate grid. And there you have it. So you have your two asymptotes drawn in, and then you draw in your parent function. So that kind of, from this, whatever this origin is, I mean, it's not your normal origin, but the origin in terms of where they both cross, your parent function would go up 1 over 1 from there, and down 1 over 1 from there, and then a half on either direction. Let's try another one. So this time, try to graph this one entirely on your own from start to finish, including getting your asymptotes on your own. When you return to the video, the answer will be revealed. So your two asymptotes are x equals -7 and y equals 3. And then our numerator is a 1, so our a value is a 1. Making this similar to a parent function. We just have to translate it. So we go our up 1 over 1, down 1 over 1, and then we go a half from there in both directions, and then we draw our line in. Now let's try a gemology application. Some diamonds are cut using ratios calculated by a mathematician, Marcel Pawlowski, in 1919. The amount of light reflected up through the top of a diamond, its brilliancy, can be maximized using the ratio between the width of the diamond and the depth of the diamond. A gemologist has a diamond with a width of 90 millimeters. If x represents the depth of the diamond, then y must equal 90 divided by x, is going to represent the brilliancy ratio, y. So let's try graphing this function. So in this case, our x, or our vertical asymptote, is going to be at 0, and so is our y. And now we can make our table of values. So we have x and y, and we can pick some numbers. So 2, if we plug in 2, we get 45. If we plug in 10, we get 9. If we plug in 45, we get 2. And then we can simply plot these on a grid. Now we don't need to worry about negative values since we're dealing with a real world application and the negatives become obsolete. So take a moment and plot these on a grid. And there you have it. This also ends our video on rational functions.